Hi students, welcome to Renju at Physics. Now we are going to discuss the third application of Gauss's law, the electric field due to uniformly charged spherical shell. That is the today topic, the field due to uniformly charged spherical shell. Electric field due to uniformly charged spherical shell by applying Gauss's law. So here we consider a spherical shell. So this is a spherical shell, it having radius r. Capital R is the radius of the spherical shell, and charge is uniformly distributed over the surface of a spherical shell. Okay, charge is uniformly distributed and it having surface star density sigma. Sigma is the surface star density that is given by Q by A, that is in coulomb per meter square. Okay. Here the charge is positive charge is uniformly distributed, so we have consider all the electric field is always normal to the surface of the spherical shell. So electric field is normal to the spherical shell. So this is the direction of electric field. Okay, we need to find out the electric field at a point due to this charged spherical shell. So we are considering three cases. The first we are considering the point outside the spherical shell, then we are considering the point is on the surface of the spherical shell, and third one, the point is inside the spherical shell. So we need to find out the electric field outside the spherical shell, on the surface and inside the spherical shell. So these are the things we are going to discuss now. First case, we are considering the point P outside the spherical shell. So we are finding the electric field at a point, that point is outside the spherical shell. So we are finding the electric field outside the spherical shell. So we consider point P at a distance P from the center of the sphere. So we consider point P at a distance r, small letter r, from the center of the sphere. So we want to find, so we are finding the electric field at a point outside the spherical shell. So we consider point P at a distance r from the center of the spherical shell. So we want to find out the electric field at the point P. So we are choosing a closed surface. Okay, so we are drawing an imaginary Gaussian surface in the form of a sphere, it having radius r. It having radius. So we are drawing an imaginary Gaussian surface enclosing the point, okay, P. Okay, so we need to find out the electric field at a point P. So we are drawing an imaginary Gaussian surface in the form of a sphere enclosing the point P. Okay, at point P we consider small area, and the direction of electric field I already told always normal to the surface. Okay, normal outward direction. So here we consider small area ds. So the direction of ds is also in the same direction of electric field. So first what we need to do? First we need to find out the flux through the Gaussian surface. First we need to find out the total flux through the Gaussian surface. By using the equation, the flux through the Gaussian surface is given by the flux phi is equal to integral E dot ds. The flux is given by phi is equal to integral E dot ds. We know that on the Gaussian surface the electric field is uniform, because if you are considering all the points in the Gaussian surface, all the points are equidistant from the charged sphere. So the electric field intensity on the Gaussian surface will be same. So I am taking E outside. Okay, before that, here electric field and the area vector ds are in the same direction. So this equation can be represented by integral E ds cos theta. E ds cos theta, but theta here it is 0. So the flux phi is equal to integral E ds cos 0. As I told, on the Gaussian surface, electric field intensity is uniform. So E I am taking outside. So the flux phi is equal to E integral ds. So we know that the value of cos 0 is 1. So we get phi is equal to E integral ds. Here ds is the small area of the Gaussian surface. So we have to find out the total area of the Gaussian surface. Here the Gaussian surface in the form of a sphere. So we know that equation to find the sphere is 4 pi r square. Here r is the radius of the Gaussian surface. Then integral over ds is 4 pi small letter r square. R is the radius of the Gaussian surface. So we get integral ds equal to 4 pi r square. So we get phi is equal to E into integral ds is 4 pi r square. So this is equation number 1. So this is the equation for finding the flux through. This is the equation of finding the flux through the Gaussian surface. According to Gauss's law, the flux through the surface is given by the flux phi is equal to integral E dot ds is equal to Q net by epsilon 0. Q net by epsilon 0. Suppose we consider the total charge enclosed by the surface, this spherical surface is, suppose we consider Q net is Q, then this equation number 2. So then the equation number 2 changes to the flux. According to Gauss's law, the flux phi is equal to Q by epsilon 0. That is equation number 3. So from equation number 1 and equation number 3, we can write, both are giving the flux. So we can write equation number 1 give E into 4 pi r square, and equation number 3 give Q by epsilon 0. Then we can find the electric field intensity E is equal to 1 by 4 pi epsilon 0 Q by r square. So this is the electric field at a point due to a spherical shell. But here I told sigma is the surface star density, sigma is the surface star density, then that sigma is given by Q by A. Q is the charge enclosed by the spherical shell and A is the area of the spherical shell. So we know that R is the radius of the spherical shell, then we can write sigma is equal to Q by 4 pi r square. So sigma is the surface star density. Surface star density is given by charge by area. Q is the charge enclosed by the spherical shell and A is the area of the spherical shell. Then here R is the radius of the spherical shell. Then we can write A is equal to 4 pi r square. So we can write sigma is equal to Q by 4 pi r square. From this we can write Q is equal to sigma into 4 pi r square. From this we can write Q is equal to sigma into 4 pi r square. This equation number 4 and this equation number 5. Okay, we substitute the value of Q in equation number 5. We get, substitute the value of Q in equation number 5. We get E is equal to 1 by 4 pi epsilon 0. Instead of Q we can write this sigma into 4 pi capital R square divided by small r square. So here 4 pi will be cancelled. So we get electric field intensity at a point due to spherical shell E is equal to sigma, here sigma r square, capital R square divided by epsilon 0 r square. Sigma is the surface star density. Here R is the, capital R is the radius of the spherical shell. Epsilon 0 is permittivity of free space. R is the distance between the center of the spherical shell and the point. Okay. So from this is found that E is inversely proportional to 1 by r square. E is inversely proportional to 1 by r square. Okay, E is proportional to 1 by r square, and here we can say that in vector we can represent E in vector form. E vector is equal to sigma r square divided by epsilon 0 r square n cap. Here electric field is normal outward to the spherical shell. If it is positive charge, electric field is normal outward to the spherical shell. Okay, so this is the equation for finding electric field at a point due to point outside the spherical shell. That is the first case. So now we are discussing second case. We are considering the point on the surface of a spherical shell. That means we are finding the electric field on the surface of a spherical shell. So here we consider the point on the surface of a spherical shell. Okay, so we already derive an equation of finding electric field at a point P at a distance r from a spherical shell. Okay, we already derive an equation for finding electric field at a point P outside the spherical shell. That is given by the E outside the spherical shell is given by outside the spherical shell is E vector is equal to sigma capital R square by epsilon 0 r square. So this is the equation of finding electric field at a point outside the spherical shell. Now we consider the point P on the surface. That means capital R is equal to small letter r. That is point P on the surface of spherical shell. So the capital R, the radius of the spherical shell, is equal to the distance between the center of the spherical shell and the point, that is capital R and R are equal. So this equation changes to electric field E is equal to, here R and R are equal, that is sigma by epsilon 0, here R square divided by, instead of small letter r we can add capital R square. So R square will be cancelled, so we get it will be sigma by epsilon 0. Okay, so in vector form, we represent in vector form, vector E vector is equal to sigma by epsilon 0 n cap. So this is the electric field at a point on the surface of a spherical shell. On the surface of a spherical shell, capital R is the radius of spherical shell and R is the distance between the center and the point. Point is on the surface, so capital R and R are equal. So the above equation, this E is equal to sigma R square by epsilon 0 R square, changes like this. So this is the electric field on the surface of a spherical shell. Now we are discussing the third case. We are considering the point inside the spherical shell. That means we are finding the electric field inside the spherical shell. So we are consider a sphere, it having radius r and sigma is the charge density. Okay, so charge is uniformly distributed. So electric field on the surface is always normal outward direction. Electric field is always normal. This is the direction of electric field on any point on the surface. Okay, so we consider a point inside the spherical shell. So we consider a point P inside the spherical shell that at a distance r from the center of the sphere. So we have to find out the total electric field at a point P by applying Gauss's law. Okay, so we draw an imaginary sphere having radius r enclosing the point P. So we have to find out the flux through the Gaussian surface. First we have to find out the flux through the Gaussian surface, that is given by the flux through the Gaussian surface is given by phi is equal to integral E dot ds. E dot ds. At the point P, the area vector will be in this direction. Area vector will be in this direction, and electric field is outward direction. Okay, that is the direction of electric field. Okay, is the direction of electric field. Okay, so we can write the angle between E and ds is 0. Okay, so we can write this is integral E ds. So the flux to the Gaussian surface is given by the flux equal to E, we can take it outside, so E integral ds. So ds is the area of the Gaussian surface, r is the radius, so integral ds it is 4 pi r square. So this equation 2 changes to the flux is given by the flux equal to E into 4 pi r square. That is equation number 3. Okay. Now we are going to apply the Gauss's law. So Gauss's law states that the flux is Q net by epsilon 0. According to Gauss's law, we can write the flux is, according to Gauss's law, we can write the flux phi is equal to Q net by epsilon 0. Q net by epsilon 0. Here, the Gaussian surface does not enclose any charge. The Gaussian surface, this is the Gaussian surface, is inside the spherical shell, so it does not enclose any charge. So the net charge enclosed by the Gaussian surface is Q net, here it is 0. So net charge enclosed by the Gaussian surface is 0. So we can write the flux is equal to, according to Gauss's law, flux phi is equal to 0. Why phi is equal to 0? The net flux to the Gaussian surface, is 0. The Gaussian surface does not enclose any charge, so Q net is equal to 0. The flux will be 0. That is equation number 4. So from equation number 3 and 4, we can write, equation number 4 is E into 4 pi r square, and from equation number 4 it will be 0. So 4 pi r square never be 0 because area never is 0. So we can write E is equal to 0. That means inside a spherical shell, the electric field will be 0. Inside the spherical shell, electric field intensity will be 0. Or otherwise we can say electric field due to uniformly charged spherical shell is 0 at all points inside the shell. That is, electric field due to uniformly charged spherical shell is 0 at all points inside the spherical shell. Okay, clear? So now we can draw a graph between, the electric field and the distance from the spherical shell. So here, this is a graph between electric field and distance, or relation. The graph between is we are drawing a graph between electric field and the distance. So here we are taking two axes. This is a y-axis and this is x-axis. Along the x-axis we are taking distance r. Along the y-axis we are taking electric field E. Okay. So we are drawing a small sphere. Here it having radius r. This is center O and it is a radius r. R is a radius. Okay. So up to r, so 0 to r, the electric field intensity will be 0. Up to this point, electric field intensity will be 0. At this point on the surface, electric field will be maximum at this point. On the surface, electric field will be maximum. Okay, on the surface, electric field will be maximum, and the distance is increases, electric field intensity will be varies. Here E is, this region E is proportional to 1 by r square. At this point electric field intensity is constant, that is given by, at this point electric field intensity E is equal to 1 by 4 pi epsilon 0 Q by capital R square, or we can write it is sigma by epsilon 0. It is given by sigma by epsilon 0. So this is a variation of electric field intensity versus the distance. On the surface, electric field intensity is maximum. On the surface, electric field intensity is maximum. If it is distance is increases, electric field intensity will be decreases. So this is about the variation of electric field intensity at a point due to a spherical shell. So we are considering three cases. One is the point outside the spherical shell, one is on the surface of spherical shell, and other one, the point is inside the spherical shell. And we got the equation for finding electric field in all these three cases. So now we are going to discuss electric field due to parallel charge sheet. How we can determine the electric field between two charge sheet, that we are going to discuss. So here we consider two parallel charge sheet of charge density sigma 1 and sigma 2. Sigma 1 and sigma 2 are the charge density of two charge sheet. Here we consider sigma 1 comma sigma 2 is greater than 0. That means both the charges are positive charge. So we know that if charge is positive, the electric field is directed outward. Okay, so here we consider E1 is electric field due to sheet A and E2 is electric field due to sheet B. Clear? So we know that electric field at a point due to a charge sheet is given by the equation E is equal to sigma by 2 epsilon 0. Sigma is the charge density, epsilon 0 is the permittivity of free space. So based on this equation, we can write equation of finding electric field due to the sheet A having charge density sigma 1, that is given by E1 is equal to sigma by 2 epsilon 0, and due to the sheet B that's having charge density sigma 2, the electric field is given by E2 is equal to sigma by 2 epsilon 0. Okay, for finding the electric field due to the sheet, we divide the figure into three regions. The first region, second region, third region. Left side is the first region. Between the sheet we consider the second region, and right side is we consider as the third region. Okay, so at the first region, electric field due to charge density sigma 1 is also acting, and electric field due to the density sheet density sigma 2 is also acting. Okay, so at the region 1, E1 and E2 is acting, but is acting towards left. And in the second region, E1 is acting towards right and E2 is acting towards left. And the region 3, E1 and E2 is acting towards right. 4. Finding the electric field in the region 1, 2 and third region. Okay, we consider a sign convention. We take, if you are taking the direction from right to left, the value is taken as negative. If left to right, all the value is taken as positive. Okay, so let's going to find electric field in the region 1. Okay, so electric field in the region 1 is equal to, by using the superposition principle, we can write E1 is equal to E1 plus E2. Okay, E1 represent the total electric field in the region 1, that is equal E1 plus E2, but we know that E1 is sigma by 2 epsilon 0 minus n cap. Why the minus n cap? Means it is acting towards the left side, plus sigma 2 divided by 2 epsilon 0 minus n cap. Okay, so here minus n cap is common and 2 epsilon 0 is common, so we are take it outside, so we get the electric field in the region 1, that is equal to minus n cap by 2 epsilon 0 sigma 1 plus sigma 2. Okay, that is the equation of finding electric field in the region 2. Next we have to find out the electric field in the region 2. Okay, in that region E1 is acting towards right, so we consider that value is positive value, and E2 is acting towards left, so we consider E2 is negative. So we can write E2 is equal to E1 plus E2, but E1 is sigma 1 by 2 epsilon 0 n cap plus sigma 2 by 2 epsilon 0 minus n cap. So here n cap and 2 epsilon 0 we take it outside, so we get E2 is equal to n cap by 2 epsilon 0 N1 plus M2. So that is a equation of an electric field between the charge plate. Now we go to the third region. In the third region, E1 and E2 are acting in the same direction, is acting towards right, so both the value will be taken as positive. So E3 is equal to E1 plus E2. E1 is sigma by 2 epsilon 0 n cap plus sigma 2 divided by 2 epsilon 0 n cap. Here n cap and 2 epsilon 0 taken as, we can take in outside, so we get E3 is equal to n cap by 2 epsilon 0 sigma 1 plus sigma 2. So these are the equation for finding electric field in the region 1, 2 and 3, okay, of a charged parallel sheet. Okay, in this way we can find the electric field due to parallel charge sheet. Is it clear? Now we are going to consider a case. Here we consider sigma 1 and sigma 2 are equal. Sigma 1 and sigma 2 are equal, magnitude are equal, but sigma 1 is taken as sigma and sigma 2 is taken as minus sigma. So the electric field in the region 1, 2 and 3 will changes to E1 is equal to 0 and E3 is also 0, but E2 is equal to sigma by epsilon 0 n cap. Okay, is it clear?